In the last video, we quantitatively defined these terms, storativity and specific storage, which refer to the volume of water that is released from an aquifer per unit volume or per surface area for a given drop-in head. What we want to do now is talk about the physical parameters of the fluid in question, water, and of the physical aquifer itself, so the rock matrix, for example, that control the magnitude of these terms. And so the first term that we're going to talk about is the compressibility of water itself. And the compressibility of water we're going to define with this term, beta. And we're going to define it as the following. It's going to be the change in the volume of water for a change in pressure. So we'll have dV, and I'll use the subscript W to denote that this is the volume of water, per the starting volume for a change in pressure, dP. So this is the change in water volume, and this is the change in pressure. And across most Earth surface applications, this term is basically a constant. Yes, it depends a little bit on the temperature of the water, but it varies so little compared to the other terms that we care about. It's basically a constant, and it's basically describing a linear elastic relationship between the size of water, how it is compressed or expands, relative to the pressure that water is under. And so it's relating strain to stress, essentially. The second term that determines how much water comes out for a change in head is due to something else. It's also due to the compressibility of something, but it's not of the fluid, it's of the matrix that the fluid is in. It's the rock aquifer itself. So this is the compressibility of the porous media. And we will define this, and what's interesting here is that the porous media expands and contracts, but it's not really because individual mineral grains are shrinking. They're, relatively speaking, basically incompressible. The reason that the porous media is expanding and contracting is because the individual grains are realigning, and so the skeleton of the aquifer is rearranging in a way that causes it to shrink or to swell. So this is due primarily to grain rearrangement. And not changes in the volume of an individual grain or of individual grains. And to think about this, we need to ask, what is the stress that's causing the rock matrix, or the grains that make up sedimentary aquifer, to rearrange? And that stress is something that's known as the effective stress. And we'll denote this sigma effective is equal to the total stress minus the pore fluid pressure. So this is the effective stress. This is the total stress. And this is the fluid pressure. The compressibility of the porous media depends on the effective stress. The way to think about this is that if you're deep in the earth and you've got a pile of rock and water above you, you're feeling, and if you're a mineral grain, you're feeling the weight of that water and that rock above you. If the fluid pressure is high, it's actually pushing the grains apart. And so there's not a very big effective stress that's felt in the grain-to-grain contacts. But as the fluid pressure drops, more of the overall weight of the overlying rock and water is supported by those grain-to-grain contacts. And so the effective stress goes up. And when we think about this in confined aquifers, we typically think that the total stress just doesn't really change very much. And so changes in effective stress are basically just due to changes in the fluid pressure. If the fluid pressure goes down, the effective stress goes up, and vice versa. And so the compressibility of the porous media, which we started talking about here, is defined as this term alpha dVt, where this is the total volume, not just the volume of the water. It's a change in volume per change in effective stress. And again, this negative sign is here just because usually we need this term alpha to be positive, and we like this term beta to be positive as well. And I'll just note so that if we were to put these two pieces together in a confined aquifer, the storativity S is equal to the thickness of the aquifer, the density of water, Earth's gravity, and then the product, or we're going to multiply that by both this term here as well as by the compressibility of the water term. But we need to add a little adjustment here, n, where n is the porosity, because the amount of storativity is going to depend on how much water is there in the first place, and we capture that with this term here. So the thickness of the aquifer, the density of water, acceleration due to Earth's gravity, compressibility of the porous medium, plus the compressibility of water times the porosity of the aquifer. Phew. So we got all these terms in here. What are some typical values for confined aquifers? Rather small. Something like 5 times 10 to the negative fifth to 5 times 10 to the negative 3. So for a given unit change in head, for a meter drop in head, you're going to get very, very little water out of a confined aquifer, which is really akin to saying that the water is not very compressible and the aquifer matrix is also just not very compressible. That's the reason that the magnitude of this is very small. In the next video, we will talk about the controls on this term for unconfined aquifers.